determination of, write down determination of the acceleration, determination of the acceleration due to gravity, due to gravity, due to gravity using the simple pendulum. Determination of the acceleration due to gravity using the simple pendulum. Okay. So we are going to determine acceleration due to gravity. Acceleration due to gravity is gravitational acceleration, right? Using a simple pendulum. So here, using this experiment, if you want to find the gravitational acceleration on the moon, you can find that, right? On the moon, if you do this experiment, you can find the gravitational acceleration there. But here, we are doing the experiment on Earth, right? So we are going to find the gravitational acceleration on Earth. But for any other gravitational accelerations also can be found using this same practical, right? I think you referred the notes. You know what a simple pendulum is, right? There's a string and there's a small bob at the end of the string, and the string is hanged to a ceiling or something. Then what do? You pull the string aside, I mean bob aside, then leave it, right? Then it causes a oscillation. That oscillation has a time period. That time period is found using this equation. T equals 2 phi L over G, right? So simple pendulum is something like this. Then it goes to this side and comes here, goes here, then comes back to the initial position. So one of these oscillation, the time taken for one oscillation is what we call a time period, right? I'm not going to explain the theories. I'm going to focus on the experiment, right? Right. So this is the equation we used in the experiment. So before doing the experiment, we have to make sure that this is a simple pendulum, not just a pendulum. This is a simple pendulum, right? So if it is a simple pendulum, let's say simple pendulum, this string should be light. This string should not have any mass, right? Not mass, I mean this should be weightless. This string, not the bob. This string should be light. Light string. And the another condition is inextensible. Inextensible. So the length of the string remains the same, right? It doesn't extend. Okay? This should be inextensible. Actually, we cannot have a light string. These have weights, right? But in order to do the experiment, we have to make sure, compared to the bob, the weight of the string is negligible. So in that case, we can consider this to be a light string. And also the string should be inextensible. So those are the conditions to make this a simple pendulum, right? Right. Then to use this equation, another requirement is upthrust. Negligible upthrust and resistive force. Resistive force should be negligible, right? Upthrust also should be negligible. You know upthrust, U equals V rho G. We have to make sure that the upthrust is negligible. So we cannot use this equation inside a liquid, right? We have to do this in air or a vacuum. Then we can apply this equation. So we can say upthrust is negligible. So for the upthrust to be negligible, you know upthrust is V rho G. Volume of the bob, this is the bob, we call this bob, right? Volume of the bob should be negligible. So for this small bob, we need a small bob. Okay, so in order to have a negligible upthrust, we need a small bob. So we can say upthrust is negligible. Another thing is, in order to have the resistive force, a small resistive force, that bobbin is small also helps to decrease the resistive force. You know, when a large ball moves through air, there's more resistance, air drag, right? But if you have a small ball, then it has a less resistive force. So under these conditions, you can apply this equation. Another thing, right? Another thing, small angle. This angle should be 5 degrees or 6 degrees. 5 or 6 degrees. You know, when you have to drag this bob to one side, right? This angle cannot exceed 6 degrees. If you exceed 6 degrees, this is not a simple, there's no simple harmonic motion here, right? We call this simple pendulum because we consider this to have a simple harmonic motion. But if you give this a large angle, initial angle, then the oscillation would be like this, right? So this type of oscillation, we cannot assume that there's a simple harmonic motion. Simple harmonic motion happens like this, in a straight line. Only if this angle is very small, you can assume that this to be a simple harmonic motion. So the angle should be 5 degrees or 6 degrees, right? Okay, just take this down quickly, right? So as I am explaining, you can take down the notes, right? If you think something is important, something on the board or something, you can take your own notes. Quickly take this down, and as I'm writing, you can take it down. And thumbs up once you've taken it down. And if you have any problem, let me know. Okay, so it seems everyone has taken it down. There is another important fact, right? These are the questions they ask in the exam, right? So here, this length is the length of the string, not the length of the string. This length is what? Length from here to here, actually. Here to the center of gravity of the bob. This length, right? This L means string plus radius of the bob. You have to think about the oscillation of the center of gravity of the bob. Otherwise, it could cause an error. Sometimes they consider the radius of this. In some cases, you can neglect the radius. But if they say you have to consider the radius, You have to consider the radius, right? So let's say a length of the string is L dash, then the length to be substituted here should be what? L dash plus R. L dash plus R, right? Draw this one as well. Put a point here. Quickly draw this. Thumbs up, right? Once you draw it. Uh, another fact is, why do we take a spherical shape? We can take like a lentil shape or something like this. But we take a spherical shape. What's the reason? For our spherical shape, the position of gravitational acceleration can be found, right? Easily. Because we need to find this exact position here. So you can easily measure this length, right? So write this fact as well. Write down in front of this uniform shape. Here we choose a spherical. What's the reason? To guess G easily, right? To guess gravitational center of gravity easily. Okay, this is like the summary, right? Summary of the conditions required there. All this is to make sure that you are using a simple pendulum. This should be not just a pendulum, this should be a simple pendulum which has a simple harmonic motion, right? So all these are based on simple harmonic motion, right? Right. Draw a line below all these like this. Just draw a line. So to again emphasize this, I'll give you a note. Quickly take this down, right? Right. Draw a line below that line, right? First point. Write down. So as you are writing, you have to understand, right? You don't have time to later prepare this. So as you are writing, understand this, right? Okay. Write down the experiment is based on T equals 2 pi L over G root. The experiment is based on T equals 2 pi L over G root. To the same line, right? It is valid for a simple pendulum. It is valid for a simple pendulum under negligible quickly take the note, right? Under negligible upthrust, comma, resistive forces and for oscillations of small angles, okay? Below that, right, number 1, under that, right, further explanation, under one, simple pendulum should be made using a string that is light and inextensible as much as possible. Okay, everyone, speed is okay, right? Right. Then the second one, right? Quickly take this down. It doesn't have to be nice letters, right? Just take it down quickly. Second one, under the main thing, second one. When Bob is small, upthrust and air resistance is lower. To the same line, right? If necessary, resistance can be further decreased if the bob is given a lentil, right? Lentil like shape. Lentil means like this, right? This shape, we call this lentil like shape. If you want, you can draw this. Then third one, write down. Pendulum is to be moved. At small angles. Within brackets, 5 degrees or 6 degrees. 5 degrees or 6 degrees. Five degrees or 6 degrees. Everyone done? Thumbs up, right, if you're done. Done writing. Right. So now I have discussed the requirements in order to make a simple pendulum, right? So those are the conditions that you need to You have to make sure that these requirements are met in order for this before doing the experiment, right? You have to consider these. They ask questions on this, right? Okay. Then we have this experiment. We do this experiment using a graphical method. Okay. So the first part is over now. Now we have to think about why do we use a graphical method for this experiment. You might not know the reason. The experiments are given, but some experiments have graphical methods. Some experiments don't have a graphical method, right? Actually, there's a reason for that, using a graphical method. Okay. Then we have to discuss that. You know that, so this is the equation, right? This is the equation. So what do we have to do? We have to find this simple g, gravitational acceleration. We can measure length, right? We can measure the length. We have to find g. We can simply measure the length. And you just give this oscillation, and using a stop clock, you can measure t as well. You can measure time period and length. Then just by substituting these in this equation, you can get a value for gravitational acceleration. You can get a value for gravitational acceleration, right? But we are using a graphical method. Why is that? Why do we have to do this same thing? Like we have to take like 6 readings, right? Then you have to get 6 different values for L and 6 different values for time in order to draw a graph. Here, the reason is to minimize random error, right? So if they ask in the question, why go for a graphical method? So one reason is to minimize random error. We can get rid of random error completely but we can minimize the random error. So what is random error? So if we take like let's say this is the accurate value, right? Right in the middle, accurate value. But in the experiment, you get values like this. So in this case, determining, let's say you got just a one value here. There's a gap here, right? But in order to minimize this, if you consider many values, in order to find the same thing, it gives us a more accurate answer. It is like finding the average, right? When you are finding the average also, rather than determining a value using just a one x and y coordinates, it is better to determine the same thing so we can make sure that the value is accurate. So graphical method is something like that, right? So we have about 6 readings, x and y coordinates, which says about the same thing. So this is, we are making sure that g to be correct value. So that is the reason using a graphical method. It is true for this practical and for other practicals as well, right? So if they ask, you just have to say to minimize random error. Right. So that is one of the methods. I give you a note on that, right? Don't worry. There's another important thing that we have to talk about. So this is 2 phi. You can write g here, like root g, and L here, right? L here. You can choose this value to be the dependent variable. to be y, right? And this root L to be the independent variable. And this becomes the gradient, simple m. So we have a y equals mx graph. In order to have the graphical method, you need to have a y equals mx, so mx plus c. But this is not correct. This is less accurate. The more accurate method is, so in the book you can see, they have squared both sides, right? Squared both sides. What do you get when you square this? T squared 4 phi squared divided by g and L. This one is less accurate. This one is more accurate. So we are choosing t squared to be y, not t. Mathematically, we can choose this one and this one as x and y. But it is less accurate, right? Therefore, we are using t squared and L to be the x. Then gradient becomes mx. So this is more accurate. Okay. This is more accurate. Okay. If you want, you can take this down. So if they ask, why do you have to square both sides? You just can say this is more accurate. We can derive why this is more accurate, right? But that is not on the syllabus. Rather than using these ones, all you have to say is this method is more accurate, right? By error analysis, you can explain why this is more accurate. But that is not necessary here. You just have to know this one is more accurate. You can take this down. This is the another point, right? Right. Below this, take down this note. You can draw a line, take down this note. For simple L and capital T, values can be substituted in t equals 2 pi L over g root and the value of simple g can directly be found. But using a graphical method, minimizes the effect of random error. So if someone don't remember those stuff, random error, system errors, I'll be doing a lesson in the future, right, on errors. Then another point, write down result gained by the graph t squared with, right, t squared with L, t squared with L is more accurate, is more accurate than the graph t with root L, t with root L, t versus root L, right? So we are going for this one, t versus root L. Okay, so that is another important fact, right? Then we are going to move for the another one. You might have heard that you have to take, when you are measuring the time period of this one, it is better to take, if you take like just a one oscillation. Let's say it moves from here, it starts from here, here, then comes here. Time for a one oscillation, we can measure using a stop clock. But this is not, this is a less accurate method, right? So what do? We measure time for a 25 oscillations. It doesn't have to be exactly 25, but recommended amount is 25, right? You measure the time for 25 oscillations. So you have to wait till this makes 25 oscillations. Then what do? You divide that by 25. That time divided by 25 in order to find the time period. So you can see this one is somewhat accurate, right? Rather than thinking about a one oscillation. So the human error, there are many errors like that. Human error, because we cannot start just right at this point, right? Stop clock. So it is better to measure the time period for a 25 time for a 25 oscillations. That's the reason there, right? So the time period is capital T, measurement is simple t. Okay. Draw a line like this above, just draw a line there to separate the above stuff. Write down y measure, y measure okay, we'll see. Write down y measure the time for 25 oscillations. Y measure the time for 25 oscillations? Question mark. Okay. Okay, so this stuff is very important, right? Carefully listen right now, right? Now carefully listen. Let's say time period. Let's say time period is capital T. Number of oscillations is capital N. If you want, you can take it down. Time for capital N oscillations. Let's say simple T. This is what we call time measurement, right? Time measurement. Take this down. You have to clearly identify these terms. So capital T is time period, that is for a one oscillation. Capital N is number of oscillations, meaning 25, right? This can be any other value. Simple T is the time you have to wait till all 25 oscillations or n number of oscillations. That this is what we measure. Simple t is what we measure, right? Taken this down. Thumbs up, right? Okay. Then we can write this equation, right? We can write this equation. Time measurement. This is the time for 25 oscillations, right? Should be equal to what? Time for a 1 oscillations times n number of oscillations. Do you understand this equation? You don't have to remember this, right? These are, you have to understand this, right? So the time measurement is time for a 1 oscillations times number of oscillations is equal to t. Then we can get delta t equals capital N delta capital T. So these two are the variables, right? Simple T and capital T. This is a fixed value, 25, it could be 40. This is a fixed value. These are the variables, simple T and capital T. In that case, you can write delta T. This can be done for any equation, right? If you find the variables, you can put delta there. If you're a maths student, you already know what's the reason. But for bio students, just remember, if these are the variables, you can put delta and make a new equation, right? Okay, so delta t equals n delta t. Then what I'm going to do is, I'm going to divide this equation both sides by simple t. So instead of simple t, I can substitute what? Capital NT, right? Instead of simple t, that is capital NT. N cancels off. So what do we get? Delta t divided by t equals delta t divided by capital T. This equation, even if you remember, it's better to remember this one. Just take this down, I'll explain what this means, right? Take this down and thumbs up. You should be able to prove this. Right. So what is fractional error? When you are doing experiments, you should be able to know what fractional error is and percentage errors, right? So fractional error is error divided by, if you want, you can take this down. Fractional error is error divided by measurement, right? Usually, for error, we substitute what? Least count. Least count. So for a meter ruler, least count is 1 millimeter, right? The least amount that you can measure using that measuring instrument. That is the least count. You substitute it here. Then this is the measurement, right? So you know, usually this fractional error has to be less than 1%, right? So what is delta t divided by t? Delta t means fractional error of simple t measurement. You have to understand these are two different things, right? Simple t means time for 25 oscillations. Time for 25 oscillations. So that is a different measurement. So in this says fractional error for simple t is equal to what? Fractional error for time period, right? That is what this means. Fractional error for simple t equals fractional error for time period. take this down. Okay. So the reason for using going for 25 oscillation is to decrease the fractional error, right? So here what is the measurement? Error means, let's say the least count. We use in order to find the time measurement, we use a stop clock. We use a stop clock, right? So for a stop clock, the least count is 0.5 seconds, right? In the lab, it is 0.5 seconds, least count. The measurement, let's say the measurement is like 50 seconds, sorry, 2 seconds. This is for a one oscillation. But if you take 25 oscillations, what happens? The denominator is higher. So the fractional error decreases, right? That's the reason why you have to go for 25 oscillations. So the measurement is larger. Then that measurement, that fractional error is equal to fractional error of the time period as well. We prove that here. Okay. Right. Take down this below everything. Take down this. Write down. By measuring time within brackets simple t for 25 oscillations rather than measuring time for a one oscillation. For a one oscillation, reduces fractional error of time measurement. Fractional error of time measurement. Draw a line below that. So I'm going to discuss the next one. Below that line, put this point. Just write this down, then I'll explain. For a certain simple L, time within brackets simple t, for 25 oscillations, should be gained 3 times 3 times to the same line, right? The certainty of readings, the certainty, right? Certainty of readings can be increased and a better average can be estimated for the time period. Okay, done. Right. So let's say you have a simple L value, right? Let's say like 1 meter. So you have the pendulum which has a 1 meter length, let's say, right? These are not exact values, just let's say. So now you have the pendulum, let's say it is 1 meter. I'll put simple L. You have to measure the time for 25 oscillations. Let's say you get T1, T2. You do the experiment once, right? For 1 meter, you measure the time for 25 oscillations. That time is T1. Then you again do the same thing, right? Without changing anything, you do the same thing. And you get another value for time. Let's say that is T2 for 25 oscillations. Then again do the same thing. You get another reading T3 for time. So these are time for 25 oscillations without changing anything, right? But due to some like errors or due to some negligence, these values can slightly change, right? You won't get this, like let's say you might get these values 50.1 seconds, another one 51.2 seconds. If you get a value that largely differs like this, right? You have to neglect that because there is a large error here, right? You can neglect that. Then you have to again do the experiment till you get a closer value. So these three values should be like this, right? Then for these values, you need to get, what you need to get is time for a one oscillation, right? So to get a one oscillation, you have to divide this by 25, right? You have to divide this by 25, then you can get T1 time period. For this one, T2. For this one, T3. Now we have three different values for time period. Then take the average of these three. How do you get the average? Just divide by 3. You have three values. You just divide by 3. So what do you get? You get a more accurate value, right? For this length, let's say 1 meter, for this simple L, you did the experiment 3 times. Same thing, right? Without changing anything. Then using these 3, you get a more accurate value for time period, right? Then next one, what do? You increase the length, let's say to 1.2 meters now. Then you do the same thing, right? You do the same, get this, then take the average. Likewise, you have to get about 6 L values, 6 time period values for 6 L values in order to draw the graph, right? So these are the what they ask in the exam, right? So here the graph is drawn between what? Not simple n and capital T. We draw the graph between simple n and t squared, right? Then the values you got here has to be squared. So you get t squared values here. You can get, then you have values for t squared, values for L, then you can draw the graph, right? You can draw the graph. Just take down this table, thumbs up once done. If you have any problem, let me know. So if you want successfully get the like full marks for those structured essays, you need to have this much in depth, right? You have to understand this precisely. Once you have taken this down, please thumbs up, right? Okay, I think you understood this completely, this table, right? Draw a line here, draw a line here. Then I'm moving on to the next fact. Then I'm going to talk about this something called locating pin. Write down locating pin. Okay. So why do we need a locating pin? So as you are measuring the time period, you need a locating pin to have a certainty of oscillations, right? So if this is the bob, the locating pin, it's something like just a pin like this. It is attached to a cork, right? This locating pin should be at the lowest point. You know that this oscillates like this, right? It oscillates like this. Locating pin should be here. Lowest point behind. Because if the locating pin is like this, you cannot clearly see whether it completes, passes, whether this string passes the locating pin or not, right? So the string is here, locating pin should be behind and at the lowest point, lowest possible point. So it cannot touch the string, right? Otherwise it would disrupt the oscillation. Locating pin should be behind the string like this. Understood? So this is the locating pin. So what are the requirements? It should be behind. Just take this down. Behind, directing to string. They asked this, right? That's why I'm giving you at the lowest position. Put a point here, then write down. To determine the turn of oscillations, to determine the turn of oscillations easily and starting and stopping instances of stop clock locating pin is useful. Okay. Right. So the oscillation happens like this, right? So you have to place the locating pin at the lowest point and direct into the string. You cannot put the locating pin here, somewhere here, right? You have to put that at the lowest point. There are reasons for that. I'll explain those. You have to place the locating pin here, right? Okay. Below that, write reasons for placing the locating pin. Reasons for placing the locating pin at the lowest point. So there are mainly two reasons for that, right? First one, you may have heard this one, right? Write down maximum speed of pendulum. Maximum speed of pendulum is at the lowest point. Maximum speed of the pendulum is at the lowest point. So you know that, right? This is just, okay, first take it down. Maximum speed of pendulum is at the lowest point. Okay, so if they ask, why do you place the locating pin at the lowest point? You just say maximum speed is at the lowest point. You know, this is a simple harmonic motion. So this is the center, right? Center has the maximum speed. Okay. But why is that? What's the reason? Do you understand what's the reason for that? What's the advantage of that? Like, how can you justify that advantage? This is the reason, right? So if they just ask the why it is at the lowest point, you can say because it is at the lowest point has a maximum speed of the bob, right? The reason is that uncertainty of the time measurement is less at higher speeds. So let's say like this, right? So let's say this is the oscillation, right? So at the lowest point, I'll just draw two positions of the bob, right? as this oscillates, at the lowest point, this has the highest speed. So time between these two positions, let's say that is delta t1, time between these two, delta t1. Because this moves quickly, delta t1 is the error due to uncertainty, right? Because we are the ones measuring, right? Once this pass this point, you have to start the stop clock. Once this pass this point, you have to start the stop clock, right? But you don't know whether to start it here or here. But that difference is very small if this moves fast. But what happens if you do the same thing somewhere here? Here it takes a longer time. So that time difference due to that uncertainty is larger for this case, right? That's why you go for the lowest position. Okay, just draw this one. Draw this one. If you are done, thumbs up. Okay, write down error due to uncertainty, error due to uncertainty, within brackets delta t, error due to uncertainty is smallest at the highest speed, at the highest speed. Okay, so that's the first one. Second one, right? Write down since the amplitude of oscillations, amplitude of the oscillations decreases uh, the bob would not pass the locating pin, would not pass the locating pin. So let's say, even though we say that there is no air resistance, there's air resistance, right? So when we are taking this for 25 oscillations, what happens? Practically, if the oscillations initial like this gradually decreases, right? Due to air resistance. So what happens if you place the locating pin here? You won't be able to take the oscillation, right? Determine that particular oscillation, right? But if you place a locating pin here, you can make sure one oscillation even after all the 25 oscillations are done, right? Understood? Okay, just quickly draw this. you have done thumbs up. Right. There's a one more point, right? There's a one more point. Okay, let's say now you have started the practical, right? So so the moment this passes this lowest point, do you start counting? Like you have to take for 25 oscillations. Do you start from 1? Like once it passes, you don't say 1, right? 1, 2, 3, I mean 1, 2, 3. Likewise, you have to keep doing this for 25 times, right? But you don't start from 1 here, right? This oscillation, because we are personally measuring that, right? It can cause a personal error. As this oscillate, you have to get used to the rhythm of this. There's a rhythm here, right? You have to get used to the rhythm. So what do? In order to get this one, let's say you measure this from 3, 2, 1, 0, 1, 2, likewise up to 25. Once this passes, once you say 0, you start the stop clock. You start the stop clock, right? Then you say 1, 2, 3, 4, 5, 6, up to 25. At 25, you stop the stop clock. So that's how you take simple T measurement, right? So you have to stay focused, right, while you are doing this experiment. So how do you say? 3, 2, 1, right? As it passes 1. Still you did not start the stop clock, right? What do? 1. You say 0. Then you say 1. 1. When you are saying 1, you start the stop clock. 1. 1, 2, 3, 4. Up to 25. Once this passes 25, you stop the stop clock, right? So that's how you take the time measurement. Okay. Draw a line below that, right? This point. When you are taking the time simple within bracket simple t measurement, time simple t measurement, the counting should start like this. Just write this one. 3, 2, 1, 0, 1, 2 up to 25. When counting 0, you start the stopwatch. You start the stopwatch. uh, count then next line, counting started from 3, counting started from 3 for the person, for the person no, when you are saying 0, when passing this point you start counting, right? For the person to get used to the rhythm, to get used to the rhythm, personal error, personal error is minimal, personal error is minimal. Okay, so you start counting from 0, right? Because 0 then 1, because you start counting when you are saying 0, then 1 oscillation, 2 oscillation, like that. Understood? 0, you say 0 here, you say 3, 2, 1. As this point passes 0, passes, you start from 0, right? Because for a 1 oscillation you have to count the time. It starts from 0, right? Time starts from 0. Understood? 0, you start the clock. 0, then 1, 2, 3, 4, up to 25. Okay? Right. Okay, so this is all I have to talked about this experiment, right? 10th experiment. Then write 11. 11th experiment. It doesn't take that much time now, right?